Last time we had the in-class, the last time we met, we had the in-class lab kind of, here's a situation, what can you do in this 2-hour and 15-minute block to understand a problem as much as possible. This problem was we had a grid layout. So an n by n grid, and it would grow as we progress through. But at any particular instance, we have, let's say, a 4 by 4 grid, and we would put in, say, a slime bomb somewhere, and its purpose is then to slime that place and the 4 locations that are right around it, right? Not on the diagonal because they're too far away, just on the cardinal directions. This is the one norm, the taxi cab way of measuring distance. All right, so one of the questions was, okay, so after the implementation, right, after they build the prototype, but one of the genetic algorithm types questions is, what would a chromosome for this look like? So what do you think a chromosome would look like?
Number of bonds used.
The number of bonds used? Well, so we could have, because not just the number of bonds, but where they are matters, right, in terms of, is this a good solution or not? And so what we could have for a chromosome is just, here's your grid, where are the bombs? 1s and 0s, right? We have our grid organized, and there's a bomb here. Or even if we didn't have it as a grid, if we just had a list of values, but then in this case, the first 4 correspond to the first row, and the next 4 to this next row, and so on and so on. And we just have 1s and 0s. There's a bomb there, or there's not a bomb there. And that would be a perfectly valid chromosome. It's all we need. The information is just, is there a bomb somewhere? What would the fitness function need to do?
Compare how many bonds it took to cover everything.
Okay, so the fitness function would need to, since we're trying to get the minimum number of bombs necessary, the fitness function would somehow, well, it would have to keep track of how many bombs we have, and at the same time, we also want to do what?
Make sure that every bomb.
We want to make sure that every position is covered, and so we would have to have something that takes away points for not having everything covered, but we would also need to do what? Take away points if things were covered too much. Right? Because there's some kind of trade-off. Yeah, I want to cover everything, but what's the easiest way to cover everything?
Bombs everywhere.
Bombs everywhere, right? But there needs to be some way of taking away points for having too many bombs. But we don't know how many bombs are the right number of bombs.
Yeah.
So what does the fitness function need to do? The fitness function can do all of the work, all of the calculations, but the idea is, okay, how many bombs did you use? Maybe what percentage of coverage do you have with that many bombs? Right? So I used 1 bomb and I have 5 squares covered. Right? So 5 of 16. So I have 1 bomb and I've covered 5/16 of the board. Is that better or worse than 2 bombs that have covered 6/16 of the board? Well, we have to think about that, right? But that's what the fitness function should be able to do. The fitness function should be able to take this kind of information, maybe just the 1 and the 5 and the 2 and the 6, and be able to determine which of these is better. So on the lab, in terms of grading it, I wasn't expecting that you would have a perfect fitness function, but just that your fitness function description thinks about these issues, thinks about what is going on, what do we need to balance. We need to balance how many bombs we've used with how much coverage we have, and somehow maybe even consider how many pieces have been double covered now. Right? At this part, at this point, we have two pieces that have been double covered. So in this solution, maybe there's a points taken away for that. So we need to think about what would the optimal score be, right? What would a perfect score be? Can we cover everything with just exactly one bump? I don't know. Maybe we can't, right? That's part of the exploration. Is there any way to have everything just covered with exactly one bomb and not have anything doubling up at all? That might not be possible. So a perfect score might not somehow turn out to exactly match this many bombs and this many things covered and everything be perfectly done. But the idea of the fitness function is these calculations are things that can be done quickly, right? The fitness function can say, okay, the bombs are here, what's covered, what's not. So it's doing all of that kind of work. We don't have to stress too much about what a chromosome looks like. A chromosome, just bomb or not in this particular case. All right, so not so much on the lab of did you get the perfect fitness function and did you get the right answers, but what was your thought process like? And that's what I'm looking for on that case, right? What were you thinking? How were you going through the process? All right, so often the way we describe the chromosomes. I mean, what happens then if we put together two solutions? If we put together two solutions, let's just go to this size board because I'm lazy and don't want to write that much. One solution might look like this, right? This is a chromosome. Another chromosome might look like this. Now, what does this one do? This one covers that much of the board. This chromosome covers that much of the board. What would happen if we then put these together? If we put these together, say, with a one-point crossover, and our crossover point was in the middle, what would we get? We get two offspring. One of those offspring looks like this, and one of them looks like this. Now, that's not the only way that we can generate offspring, right? But this is a way, right? Just take the first half from here and the second half from there, first half from here, second half from that one. And so what about this child? Not good at all, right? In terms of solving. What about this one? Solves the problem and actually gives us a best answer. But when we look at that best answer, we have a bomb here, here, and here. What was it? Yeah, so these spots get slimed twice, and each of these get slimed just once, but it's an optimal solution. So our method that we have for analyzing that, our fitness function, shouldn't take off too much for sliming things twice. What happens if we had the other solution that we could think of? I mean, other than just rotating the board around, but the other solution, what happens? Again, these two get slimed twice. You can't really get around that in this case. So the fitness function shouldn't take off too much for sliming something twice. On this size board. Should it on a bigger size board? Maybe, right? Because maybe there are fewer and fewer things that should be slimed twice. So again, the idea is thinking about the process. What's the hard part here? The hard part in this case might be coming up with the right fitness function. The crossover method in this particular case, if we just happen to have this, then we get an optimal solution after just one generation. What would have happened, though, if we had that one and this one instead? then the 1-point crossover in the middle will do what? Will alternate back and forth between this answer and this answer, right? And it will never get us to a better answer than that. Right? So 1-point crossover at this location isn't necessarily a good thing. Well, what if we picked a different location for the 1-point crossover? Well, if we happen to pick here, then we would get a solution after one generation. If we pick somewhere else, then maybe not.
One thought I had is that for my fitness function, I didn't really look at whether it's on twice. I just looked at the amount of bombs you're using and the amount of tiles you're covering.
Okay, so what would happen if we just did that and then we ran our genetic algorithm, just how many bombs are you using and how many tiles are you covering? What do you think that it would tend toward? What kind of solutions would be good? Sounds like putting a bomb everywhere would maximize that value, right? And you would end up with more bombs than we would like to have. So if there has to be something in the fitness function that is taking away points for some problem, right? And so what that is, we get to think about it. But the idea is that the problem itself, as far as the chromosome, and it seems like a lot of people spend a lot more time describing what the chromosomes would look like than they did on what the fitness function would look like. And in this case, the fitness function is the more important part, right? Because the chromosomes are just, hey, is there a bomb there? Yes or no? Could you have a different way of describing the chromosome? Sure, you could have something else, some other way of doing that would change than what your fitness function looks like. But what we're looking for is something that is easy to operate with, right? Something that's easy to think about. All right, so this is the...
Pulled it up, and the solution I use is 2 times, the fitness function is 2 times the amount of tiles slimed minus the amount of bombs minus the total grid size.
Okay, so you did 2 times number slimed minus the number of bombs.
And then minus the total number of tiles.
Minus, and so if we had an n by n, so it would be n
squared.
N squared. All right, so you do have some penalty for using too many bombs, and then there's some penalty.
It's for unslimed tiles, because you raise the score by sliming more tiles, basically.
Okay, so this is a penalty for leaving things not slimed?
Yeah.
All right, so this kind of idea is what we're looking for, right? Somehow finding a right balance of sliming things, but not using too many bombs to do it, and leaving as few things as possible. And so what would we like to have? Well, what kind of values do you get in this particular case? What if you slime everything? What happens if you slime everything?
Like put bombs on every tile?
No. What happens if everything got slimed? What would you have? Well, the number slimed would be n squared, right? The number of things. So we would have 2n squared minus the number of bombs minus n squared. So what would you get? You would get as your biggest possible value n squared minus the number of bombs. So what happens? If you have more bombs than you need, you don't get rewarded as much as if you did the same thing with fewer bombs.
And at the same time, this function makes it so that in this 2x2 grid, I noticed that an earlier version of the function would potentially reward the genetic algorithm for not bombing the last tile, whereas here now the AI says that you might want to avoid bombing only one tile, but you should still bomb one tile if that's what you have to do.
So does that make sense? So what do you get? You get your highest score possible is n squared minus how many ever bombs you need. So what happens if you use too many bombs? That score is brought down. Fewer bombs, that score goes up. What happens at the optimal situation? This number is as high as it can possibly be, whatever that happens to be. So that is a fitness function that will take care of it, right? That will do what we were wanting to do. Are there other possible fitness functions? Sure, there are other ways to achieve this kind of goal. So what does this one do? It doesn't reward you for putting a bomb everywhere, because what happens if you put a bomb everywhere?
You get 0 points.
You get 0 points. What happens if you did it with fewer bombs? You get more points, and so that score is a better score. Right? Putting bombs everywhere, or putting what happens if you put no bombs?
I think you get a negative score.
Yeah, you can get a negative score, right? If you leave things unslimed, you can get a negative score, because these values could account for that. And so you can go from a negative score, if you put no bombs at all, you go negative n squared, and your highest score possible is n squared minus whatever the optimal number of bombs happens to be. But we don't know what that number is, but what will the algorithm hopefully then do? Find that number for us, right? Hopefully the algorithm will not settle into bad solutions. But again, that's going to depend on how we do our crossover. What would mutation look like? What would mutation look like in this case?
Maybe we have a chance to randomly flip one tile.
Yeah, maybe we have a chance to just randomly flip a tile. Say, put a bomb if there was one, or take one away if there was one, right? You could just pick a spot and randomly do something. What might happen if you add a bomb in? You might now be able to cover things that you couldn't before, and your score goes up. What happens if you take one away? You might still leave the same number of things slimed, but this goes down, and so you get a better score, right? And so this part is a smaller number, so you're subtracting something smaller. So turning one on or off might be beneficial. And so I didn't ask you to try to implement a genetic algorithm in this case, but now we're starting to see what would happen once we have what a chromosome looks like, and once we have how our fitness function works and what it needs to do. Now, what does it need to do? The fitness function isn't just this, because in our genetic algorithm in the program, it has to be able to calculate how many things are slimed, right? It has to be able to see how many things are bombs and so on. So it has to be able to actually carry these steps out. But we can do that based on, since we know where the dots are and how they are relative to each other. Oh, there's a bomb here. Okay, what's covered and what's not. Make sense? So what does it do? This means that we can kind of trial and error our way through to solutions. And that's what a genetic algorithm is doing. It's guessing and checking. But then it's not just guessing everything. It's not just guessing every way that you could put one bomb, and every way you could put two bombs, and every way you could put three bombs, and so on. What is it doing? It's starting with some ways of putting bombs. Probably for small boards, a very limited number of the ways, because there aren't that many ways to do it. But a very limited number. And then as the board gets bigger, still just starting with a very limited number and trying things and producing hopefully better and better potential solutions until it either gets to a situation where this value doesn't change for a long time, or until we get to a point where somehow we knew that this value was the biggest that we could possibly get. But we don't know what the number is, so we would have to use one of the other alternate ways of ending. Right? Either it didn't change for a long time. What other ways do we have to end a program or end a genetic algorithm? If this number didn't change for a long time, we might say, okay, well, that's the best we're going to do. Or set number of generations. Or if the population itself hasn't changed, if the values in the chromosomes aren't changing at a certain point, right? So not only is the number not changing, but the chromosomes themselves aren't changing. We didn't talk about that method, but that's another possible way. But generally, what is it? If this number has stayed the same for a long time, or if we've said, okay, we're going to do this for 500 generations, and then we reach the end of that, okay, that's the best we can do.
Or you could design a fitness school to have a max number that you know.
But we can only do that if we know what the max actually is.
Or you design it to.
Or if we design it to just exceed a certain value and say, if we get this close enough, we're going to say we're done. And so that's possible. And in some situations, when we know what the target is, but we don't know how to get to it, then it's beneficial to put an actual number in place. But it could be beneficial as a stopping point to say, okay, on this size board, I think I can do it with this many bombs. Let's see. Okay, if I get to this value, then I will call it a day, and that's a possibility. All right. So what do we have? A lot of different ways. But what are all the pieces? Now we think about the whole genetic algorithm structure. And if you break it down piece by piece, I mean, it looks like there's a lot going on. You look at the handout. There's a lot of stuff on there, but really it's all just one piece at a time, right? This piece, this piece. So what does our chromosome look like? What does our fitness function look like? How do we calculate that fitness function? If this is what our fitness function looks like, how do we then calculate that in terms of what a chromosome is? So we have some work behind the scenes to actually calculate how many things are slimed. But we've already done that work because we built our prototype that it says, oh, this thing is slimed. Right? So you put bombs here. Okay, this thing is slimed. This thing is not slimed. What's the difference in terms of running our prototype as a genetic algorithm? Instead of using our mouse interactions to set the bombs, what would we use to set the bombs? A chromosome like this, right? Just some text input, and say, here's the bomb, here's a bomb, here's a bomb that could be created internally. Just here's a chromosome. Here's where bombs are in this particular individual. Here's where the bombs are in this particular one. Here's the bombs in this one. All right, so makes sense? I really like this problem because it is useful in so many different ways. It's useful in the beginning. I used it in 1803. In 1803, we do this on one hand just for the interaction with the prototype version, right, of building the interaction with the user. Also in terms of being able to calculate distances using one norm, so using vectors to see if things are, how close they are. So there's that mathematical aspect. In an algorithms course, counting solutions, how many solutions are possible and so on, right? Developing algorithms that are not genetic for that purpose. And then here, changing the problem to be able to see how that genetic algorithm approach applies. So I like the idea of one problem that you can start in first year and still learn something from it. I don't think you all saw it in first year, but it's a problem you can get in first year and then still learn things in different variations throughout. All right, so we also have talked about the mastermind approach, what a chromosome looks like in mastermind. And what does a chromosome look like there? Well, you know how many digits there are, so just make up that many digits, right? That's what a chromosome looks like. The fitness function. In that case, the fitness function does know what the right answer is and gives you back information. What happens when the fitness function doesn't know what the right answer is? Then we get this kind of situation. We don't know what the right answer is. We won't know what the right answer is until after the algorithm finds it for us. Right? And assuming, well, until after it finds it for us, assuming that it can find it for us. But in this situation, it should be able to find an answer, either, hopefully one of our stopping conditions. And sometimes we do need all of the stopping conditions, right? We need to have, if you get to this point, go ahead and stop. If not, then stop when you get here. And if not, stop. Because what could happen, what conceivably could happen, is we get the best answer in some generation, and then, but in the next generation, it goes back down again. So it doesn't hold the best answer for 2 in a row. And then it goes back up, but then it goes back down because some kind of cycling happens in our chromosomes. And so we never reach the stopping condition that says we went this many generations without changing. So maybe we say we went this many generations without going above our previous best, and then we're going to return our previous best. So that could be a situation. We end up with an answer that goes up and down, up and down, up and down. And so we never reach that, oh, you haven't changed for a long time. Well, if we did the number of generations, what if we picked the wrong number of generations? What if we stopped too short? Or what if we pick the number of generations, stop there, and give out the best answer at that time? That might have been in one of the dips. So we might not give the best possible answer. So there's some tweaking about what do you do at the stopping point, and we have to decide and think about that. Again, sometimes we don't know that until we've tried the algorithm and we realize, oh, this is what's happening. Let's change it a little bit in terms of what our stopping condition happens to be. All right, so for mastermind, the fitness function already knows the answer, right? So that side has kind of created or given the problem to the AI, which is not the way we're typically going to use them. We're going to use them in a situation like this where we don't know the answer, and other than just trying a bunch of stuff, we don't really have a better approach right now. What about with the Queen's problem? What should a chromosome look like for the Queen's problem? All right, so we could make it look like that, right? If we had an 8x8, because it's an 8x8 board, so we could have 64 spots, and say there's a queen here or not. And then the function could determine whether the queens are attacking each other or not. But let's think about a better way, a more condensed way to create a chromosome for the Queen's problem. What do we know about the board? In a solution, how many queens can be in the first row? Just one queen. Right? So I'm going to start from the top. I don't know why. We'll start from the top and just call this, number the rows. We can number them 1 through 8 or however you want to start your indexing. We number the rows. And then what? We could do the same thing for the columns. And then we could have a chromosome create just a list. Just create a list. Row 0. Give me a number. Give me a number from 0 to 7. Tyler, give me a number. 5. What does that mean? That means that the queen is right here. Give me another number, somebody. 2. What does that mean? That means that this queen is right here. What if I went 2 and 5 again? That would mean queen's there. So what do I do? We need 8 numbers. And what would that correspond to? Queens being in that row, that column. So what happens? Instead of a chromosome being 64 bits, what is it? Just 8 numbers. Again, is it still 64 bits? Yeah. But what happens as far as us working with it? It's easier for us to work with. Right? Does that make sense? And so we could have a list here, a single list that says this row and this column. Right? So the index is the row, or you could make the index the column, whichever, right? But you make the index one of them, and then the value there is the other. Now, what happens in this particular case? What do we know about that solution or that partial solution so far? It's terrible because there's a lot of attacks, right? The 2 queens attacking each other because they're in the same columns. But that's something that our fitness function could then take away points for. What would our fitness function also need to be able to do? Fitness function should also not just look at if there are 2 numbers that are the same, that means that they're in the same column attacking each other, so lose some points for that, but also be able to analyze the diagonals. So how could you analyze diagonals? how could we easily calculate things to see whether things attack on a diagonal? Let's put something. Let's see. Let's put one here. Yeah. So what happens if here we have something in 3. Right, so what happens here? Here's the index values of these two, 3 and 5. And here are the actual values. The difference in the index, 2. Difference in the values are 2. What did that mean? That means that they're diagonal. Now, what would happen if it's diagonal in a different direction here? So in 7, we had 5. It's absolute values there, right? Because it could be diagonally this way or diagonally this way. So if the absolute values of this difference is the same as the absolute value of this difference, then they're attacking each other. And it doesn't matter where they are. And so what happens? We can easily calculate to see if things are on the diagonals. How do you see if they're on the same column? Check to see if the numbers are the same. How do you check to see if they're on diagonals? This absolute value aspect. How do you check to see if they're on the same row? They can't be on the same row because what happens? Our chromosomes only allow 1 per row. So we don't have to check for that. Which is much nicer than not only with the 60. So we end up with the 64 situation. We'd have to check to see if they're on the same row, the same column, and the same diagonal. All right, with this approach, okay, ultimately we're using the same number of bits, but we're saving some work. We don't have to check the rows anymore. All you have to check are columns, are the same values in here, and are they attacking on diagonals?
One thing you could also do is distribute numbers between 1 and 7. Instead of randomly getting every number, you could just distribute 1 to 7, because you also know they can't be on the same column order. Okay,
so what if we wanted to specify that the numbers, we wanted for the initial populations, we only had the values 0 through 7. So we didn't have the same column situation. What happens if we do that? Let's say I have a solution. Okay, there's a potential solution. There's a member of our population. Now, what do we know about it? We're hitting diagonals all over the place, right? Because what did we do? We just put the queens right down the diagonal. So everyone hits everyone in terms of that measurement because we're ignoring the things in between, right? All right, but that fits that portion of having no row. We don't have to check rows and columns at all. And here's another solution. It looks like that, or another potential solution, right? This satisfies that. Now, what does that one do? The other diagonal, right? The queens are on the other diagonal in that case. All right, so we have these two solutions, or these two members of the population. They're potential solutions. They have very low fitness scores because we're taking away points for having collisions. Let's look at now combining these in, say, a crossover method. What happens with the crossover method? If we pick a 1-point crossover, for instance, let's say we cross over here. What happens? We end up creating row or column collisions. We still don't get row collisions because of that situation, but we end up creating column collisions even though we started with no column collisions at all. So what do we have? We wouldn't want just a point crossover, like a single point crossover, if we wanted to maintain that, right? So even if we started with no column collisions, again, the structure itself eliminates the row collisions. Even if we start with no column collisions and then went to 1-point crossover, we could immediately introduce those collisions. And so what would we need to do? Maybe find a different method. And so what you might want to think about before Thursday is what we might be able to do in that situation to avoid, to maintain that no columns being able to collect. We already have no rows. Make sure that you can avoid no columns. So we want to think about that a little bit. John?
Do fitness functions only work with like two possible solutions? Just only one solution?
A fitness function only gives a score for a particular one chromosome, one particular solution. So the fitness function should give a score for this. Now the crossover, where we're combining parents, if we're maintaining the genetic situation of two parents creating offspring, then we need two chromosomes and put them together to come up with the new ones. But as far as the fitness function is concerned, it takes one member of the population, one thing, and scores it, gives it a value. So what should happen here? This shouldn't lose any points for there being row or column collisions, but it should lose points for the diagonal collisions. And so we need to somehow take away points for having any diagonal collisions at all. How you want to do that is, it's partially up to you. I mean, it's completely up to you, but there are better ways than others, but you want to think about that. There has to be some penalty for having those collisions. If you had no collisions, then what's the perfect score? What should a perfect score be in this, on this board? Well, number of collisions would be taking points away from the best. So what should the perfect high score be? 8, right? Should be 8 because that's how many queens that are the best answer, which we know somehow else, right? We know that from externally. We know that you can put 8 queens on, and that's best possible. What if we went to a 20 by 20 board? Well, I told you that you can put 20 queens on, so we know the best answer is 20. But what if we didn't already know that? Then we would have to have some other aspect of our fitness function to account for. What if you could somehow fit more? But what do we know? We do know that 20 is the best possible, even if you can't get 20, because you can't have more than one on the same row and more than one in the same column. So 20 is the best possible answer. Whether or not you can get 20 is a different question. So what could we set in our score? We could say, if you ever get to 20, stop. You might not ever be able to get to 20. You can, but I mean, that's something we know separately, right? But we do know you can't get more than 20. So we could have, in that case, have our built-in that says, here's the, if you ever get to this, then you stop. We made it. If you don't get there, then maybe you stop after 1,000 generations. Does that make sense? All right, so what happens, though? We want to think about, is there a way to put these chromosomes together that don't have row or column intersections and maintain not having row or column intersections? Right? So that somehow, just by putting these together and following the same kind of method all along, that we never create that conflict.
So, sorry, when you're making like new children, you can't just like take an adult and edit it. You have to like combine two.
Well, okay, so you do have, there are versions of genetic algorithms that involve this kind of asexual creation of the offspring that takes one parent and creates offspring from it. But as far as maintaining the traditional genetic algorithm situation, it's two parents to create the offspring. There are versions that have more than two parents, and you could do something with fewer, with just one parent. But it's not kind of the traditional genetic algorithm approach, because the idea was that it's inspired by biology and inspired by that sense of having two, whatever they happen to be, taking genetic information from one, genetic information from the other, and creating something from there. So it's not that you can't have things from just one. It's that it's not the typical, at least in the traditional genetic algorithm context. What could you do in terms of one parent? What could we do? We could just keep permuting things, right? We could just keep jumbling them up. And what would that eventually do? Eventually, you will find a layout that works and has all of the queens in the right spot. But how many permutations of 8 things are possible? How many ways are there to jumble up 8 things? 8 factorial, right? Because so I mean, we could just go through all 8 factorial possibilities and we will find an answer in there. The point is, though, if we have a certain number of potential starting solutions and we combine them in just the right way, we might be able to get to that solution much, much more quickly than trying all 8 factorial possibilities. And then if you go to, say, a 20 by 20 board and you're trying to find a solution, 20 factorial is kind of big. I mean, we can still go through it pretty quickly with, an efficiently written program. But you get a big enough size board, and you can't even do that, right? Unless you just happen to get really lucky and find a solution early on. But remember, on the 8 by 8 board, there's a lot of ways to list those, we said. A lot of ways to put queens, and a lot of ways that aren't solutions, right? There are very few solutions. But in this formulation, it's a little bit easier. There are fewer possibilities, and so for the 8 by 8, we can get there much more quickly. But in other situations, as the board gets bigger and bigger, usually drawing from 2 potential solutions and creating new ones from there is better. So think about how we could guarantee that if I had not just these 2, but any situation where you had the numbers 0 through 7, or 1 through 8, however you want to number them, but you have those 8 values, and there's no duplications, but then you're putting 2 of them together, is there a way to guarantee that you don't get duplication inside there? Right? Because what would speed us up in terms of the fitness function? It would speed us up if we didn't also have to check. We have already now avoided row collisions. If we don't have to check column collisions, then that's nice, right? It just speeds it up a little bit. Can we avoid needing to detect diagonals? That's harder, right? That we have to do. We have to do that check to see the index difference, the value differences. Are they, absolute value-wise, are they the same? If so, then you either have a collision in this direction or a collision on the diagonal in this direction. What would happen if we changed it from a square board to a rectangular board? Well, we still have the idea of how many things can you put on there. What would the maximum be in that case?
The amount of the smallest size.
Yeah, the smallest side, right? Either the smallest number of rows or the smallest number of columns. And so the problem changes a little bit, but the underlying ideas are the same. What about the diagonal attacks? Still the same, right? It's just now we have the smaller of the 2 values are possible. What if we had the board wrap around? What if it wrapped around this way? So we had a cylindrical. Would it change much? That wouldn't change much, would it? As far as just wrapping around this way? Because if you could attack somebody going off that way, you could have just attacked them going the other way as well. So that doesn't change anything. What if we just wrap top and bottom? Same thing. What if we wrap top and bottom and side to side? What kind of shape do we get? We get a torus, right? We get a donut. Then what happens? Then what happens when you go on a diagonal? The diagonal wraps around the donut. So then you do have to do some other checks. So then it does get more complicated in terms of, are these two things attacking each other on a diagonal? So around the top and bottom, that doesn't change much, but the diagonals now are wrapping around. I can't, whatever, it's changing my direction as I go around. Right, it's wrapping around the donut all the way in the hole and out, back in and back out. Okay, so think about how you would want to guarantee that you could maintain this kind of situation, right? Maintain the different indices. Because if we do that, then we don't have to worry at all about rows or columns. It's just the diagonal checks. And then our fitness function would need to somehow say, I want to have a penalty for having any collisions, right? So what would the high score be? Instead of, in his case earlier, it was like n squared minus, well, it was, you had it set up as 2 times the number of slimed minus the number of bombs minus n squared. And so the high score would be n squared minus the number of bombs.
Are we assuming that he's trying to fit exactly 8 queens?
Well, so what happens? We know that you can't fit more than 8. So 8 could be the high. So if we did fit 8, we know we've made it. We know it's perfect. But we could start with 8 and then subtract something for number of collisions, right? What would happen in this situation? How many collisions do we have? So it depends on how we count the collisions, right? Are we counting the collisions 0 collides with 1 and 1 collides with 0? Or are we just counting the collisions one time?
49 is the maximum number.
Right? And so what happens? This number can get pretty small, right? Because this is a big number, so 8 minus that can be a negative number. And then what happens as you reduce the number of collisions? This gets closer and closer and closer and closer to 8. And what if you avoided all the collisions? It would be 8. And that solution, or a solution that had a score of 8, would be an answer to the problem.
Take out the constant, say the highest score is 0.
We could do that. We could do that and say the highest score is 0, and then you're just losing points for every collision that you have.
That would be very demoralizing if this wasn't high.
You worked really hard and you got back to 0. Well, what's the benefit of having this there? The only benefit would be that the score would correspond to, in some way, to the best answer. But again, yeah, there's nothing that says you have to have the 8. You had to have it in your version of the problem because you were giving in the other problem, you were giving points for having slimed things. So there had to be something positive for that. In this particular case, I mean, what if we didn't know that the answer was 8? Maybe we have something like number of queens minus the number of collisions. I don't know if that would probably lead to a different problem, right? That would run into something else where it would optimize things by not putting any queens at all, right? Just don't put any queens at all and you get a 0. Except what would be higher? Higher than that would be if you had 8 queens and no collisions. So even I think this would take care of it. right? So if we didn't know that you could put 8 queens, we could say, how many queens have you put on the board minus how many collisions have you had? And the higher the score, the better you are. So yeah, that would be a fitness function in that case that would work, even if we didn't know that the right answer was 8. And this would even work on some of the boards that are smaller than 8 by 8, where you can't get that many. So this approach would be beneficial. Question?
I was going to ask, in the way we have it set up where it's the list, could they even have like, oh, I'm just not going to put any queens down, or does that enforce a queen's?
Well, the way we've set up our chromosomes, it would enforce that since you have to have numbers there, so the algorithm wouldn't be able to not put any queens on at all. So that the way we set the problem up would take care of it. But if we hadn't set the problem up in exactly that way, in like the bits way, where it could have all zeros, even then, this would take care of that and give incentive to put some queens on the board. And it would lead toward the best answer would have 8 queens, no collisions. So yeah, if we had organized the problem in the like we did with the previous one, and it's just, is there a queen here, yes or no, then that would, this would still, potentially you could have no queens, which would be just fine on the no collisions, but it would still be a score of 0 because you have no queens. So, and one queen would be better than that, and 2 queens would be even better than that. But 2 queens and 2 collisions would be the same as having no queens. Whatever, right? But if we're only counting collisions one way, then that wouldn't happen either. But 2 queens and 1 collision would be better than no queens with this method. Would that be right? I don't know. You have to think about that. Was that a better scenario? But this method would allow you to get to the right answer of having 8 queens and no collisions at all. Does it make sense? All right, so where are we? I think there are a lot of details in the handout that we don't need to, that won't be on the quiz. If we haven't spent a little bit of time talking about it, there's some methods that I talked about for crossover, and there's some other methods for various things. If we haven't at least mentioned it, then it won't be on the quiz. But the quiz is intended for more of the higher level approach of genetic algebra, understanding the concepts, understanding what might you do in this case, what might a good fitness function look like in different situations, and so on. So otherwise, we have lots of lab pieces still out there to work on, and so we will stop for now and give you a chance to work on those and ask any questions that you like.